Okay, the second topic that we have today is on solids. So you again have a two-page handout on solids. The top drawing is exactly like the first two for gases and liquids. Kinetic pertains to motion, the assumption that particles of matter are always in motion, and then you can draw a little diagram of solids, liquids, and gas. Okay, for solids, particles that are closely packed together in fixed positions and only vibrate in place. Solids have a definite shape and a definite volume. The intermolecular forces of attraction are much stronger in solids than in liquids or gases. And solids have the lowest amount of kinetic energy. Since kinetic energy is about motion, solids don't move, they vibrate in place. Fluidity, solid particles vibrate around a fixed position, they do not flow. Density, the densities of solids are higher than liquids and solids. I'm sorry, it should say than liquids and gases. Solids are more closely packed together than either liquids or gases, so that makes them more dense. Generally, solids are considered incompressible. You can't squish them and make them smaller. Crystalline solids, most solid substances are crystalline. A crystal is a structure in which particles are arranged in orderly, repeating, three-dimensional patterns, and that's called a crystal lattice. The shape of the crystal lattice reflects the arrangement of the particles. Different types of crystalline solids, ionic crystals. The ionic crystal lattice consists of positive and negative ions in a repeating pattern. A good example is table salt, sodium chloride. Sodium chloride in your salt shaker looks like little squares. You can crush it up, look at it under a microscope. It will still be little squares because the particles are always arranged in the same way. Covalent network crystals. This covalently bonded network includes a very large number of atoms, and an example would be a diamond. It's pure carbon, but it's formed under extreme pressure and heat. And so a diamond will have a large number of atoms in a particular network. Metallic crystals. Metallic crystal is made up of metal cations. Remember, that's the positive charged particles with a sea of electrons. An example would be any metal cube, copper, iron, gold, silver. Covalent molecular crystals, a crystal structure consisting of covalently bonded molecules held together by intermolecular forces. Examples here would be ice, the way ice crystals form, sugar crystals, iodine forms crystals. Those are all covalently bonded. Okay, on the back, or on the second page, there are two types of solids. So we covered the crystalline ones. The second type are amorphous solids. It's from the Greek word meaning without shape. The particles of an amorphous solid are not arranged in any particular order. Examples, glass, rubber, plastics. Those are going to be mentioned in the movie with the worksheet that you'll be watching this weekend. So this pertains a lot to the new NOVA that was on. Amorphous solids are arranged much like liquid particles, but they are in fixed positions. Amorphous solids do not have a definite melting point, but crystalline solids do. Now, if you can get to the PowerPoint, if not, we'll look at it in class on Wednesday. There is a picture of crystalline solids versus amorphous solids on slide 9 in the PowerPoint. And if not, I will show it to you in class if you can't get it to load, since we're having some computer problems. The very last question, what type of crystalline solid has the highest melting point? That's the covalent network crystalline solid. It gives you examples where we think of metals as melting at high temperatures, but something like graphite can melt at a much higher temperature. That's all the notes for today.